Yeah, so I think we're going live now. So.
Okay.
Yeah, okay, I think we're live. Hi, everyone. Thank you so much for joining us today. My name is Stephen Oladele, and I welcome you to today's workshop with Ankur Patel. I'm going to be introducing Ankur Patel, and then he's going to be jumping right into the workshop because, of course, we don't want to waste your time. But thank you so much for joining the workshop today once again. And Ankur is going to be, we're going to be pretty much introducing the workshop. Ankur is going to jump into the workshop, and then we'll have a session for a Q&A later on. So yeah, once again, my name is Stephen Oladele. I'm the lead volunteer for AI School Africa. So what we do at AI School Africa is we provide quality content that make accessible quality content, and opportunities in the areas of data science and artificial intelligence. And this is one of the offshoots of such course we have. And in today's workshop, we're going to be having natural language processing, an introduction to you, and basically a hands-on workshop for you to get started with natural language processing as well. So we're going to have Ankur Patel, who is the founder and head of data at Glean. Glean Analytics is a solution you should check out. I think they apply analytics to pretty much financial data for businesses and really help optimize their business operations, and something you should check out as well. He's also the author of one of the best-selling books on unsupervised learning, as well as the author of the newly published book, Applied Natural Language Processing in the Enterprise. Without further ado, this session is going to take right about an hour or so. But without further ado, I'm going to hand over the session to Ankur now to take on. And then we hope you learn enough. So please engage in the comment section, introduce yourself as well as what you hope to learn from the session as well. And then we'll take everything up to there. So drop your questions too. Right after the session, we have a particular period for question and answers where you get to interact with Ankur in real time. And then we'll carry on other things from there. So thank you so much once again for joining this session. So I'm just going to hand over the presentation now to Ankur, and then enjoy the presentation. Yeah.
Thank you, Stephen. I really appreciate that intro. And without further ado, I can go ahead and share my screen here. I will go through the course in more detail. So again, this is an applied course or workshop rather. We will go through different elements of natural language processing, including some of the latest and greatest in this space. This is adapted from a course that I actually teach with the ODSC organization. So they're the Open Data Science community. They're a global community. I think you should check them out if you haven't already. And it does derive heavily from the new book that I published, Applied Natural Language Processing in the Enterprise, which is an applied book. So a lot of the content there is for practitioners that want to take NLP and apply it to real world problems as they build applications for their organization. In this particular workshop, we'll cover 3 big modules. We'll intro NLP. This really just brings NLP into perspective for those of you that are perhaps newer to this space. What is NLP? Why does it matter? How is it used today? And what sorts of applications? I think once you have awareness of NLP in the world around you, you'll have an appreciation for sort of how this actually comes together and really sort of how the technology works under the hood. In module 2, we'll cover the basic foundation of NLP. Now, a lot of basic NLP isn't done in the same way that has always been done. So a lot of the basic NLP that we'll cover in module 2 is done automatically using neural networks. But it's very important to understand the basic building blocks of NLP because it helps you appreciate sort of just how machines are taking text, for example, breaking them apart, and then deriving all the applications that NLP is able to produce. So understanding the basic building blocks will be foundational to your understanding of NLP, and it will bring us to module 3, which is taking the state-of-the-art versions of NLP using neural networks. Neural networks, as many of you already know, they're black boxes, but they're really good at function approximation. So they can actually model different scenarios automatically by learning different relationships and then solve really complex tasks, not only in NLP, but certainly also in computer vision. And so a lot of the basic NLP that we will cover in module 2 is now done automatically by large neural nets, and we'll apply those neural nets in module 3 to build a sentiment analysis model for IMDb movie reviews. So a little bit of background. I don't want to go over this too much, but I'm the author of 2 books, as Stephen said, Applied Natural Language Processing in Enterprise. The other book is Hands-on Unsupervised Learning. I'm founder of a startup, a fintech startup called Glean, and I've run machine learning teams at several startups to date. So I have experience applying machine learning to real-world problems. And what we want to cover in this quick workshop here is we want to go and retrace at least some of the major developments in NLP over the last 70 years, especially the applications that exist today in the most popular forms. We will also touch base on the 3 major software libraries in NLP today that are modern and are really scalable libraries for us to use. And they're spaCy, fast.ai, and Hugging Face. So those are 3 that you'll come across very often if you're doing NLP today. We'll use spaCy specifically to perform some of the basic NLP tasks. Many of these should be at least remotely familiar to you. So tokenization, part of speech tagging, dependency parsing, and such. And then we'll finally get into the kind of the more advanced portion, which is the neural network portion, using pre-trained language models that have come to light, especially in the last 3 years. We'll use those pre-trained language models to perform transfer learning, and we'll actually even fine-tune a language model on IMDb movie reviews and use it to train a better version of a sentiment analysis application. So let's start with module 1, just a light intro to NLP. Now, a lot of the material that you will see here is covered in much greater detail in my book, as well as the course that I do with the ODSC organization. So you can turn to either of those if you feel like this is not enough depth. But what I do want to do as part of this workshop is build high-level intuition around NLP. And then I think a lot of the details we could save for later. So what is NLP? So NLP is a branch of computer science that deals with natural language. So you can think of as language that is spoken or written that we as humans use to converse with one another. Natural language is separate from, say, programming or computer language, and that's really the kind of major difference. That's why we call it natural language processing as opposed to, like, for example, computer language or programming languages. And natural language, even though we focus a lot on text, it covers things like speech recognition, and it also covers comprehension and just NLG, which is generating new natural language. So NLP is like this all-encompassing field that has elements of NLU, so natural language understanding, as well as NLG, natural language generation. The popular applications in this space are in a machine translation. So think of Translate by Apple or Google Translate. Those are very popular applications. Speech recognition and question answering. So think of Alexa, Siri, Google Home, Google Assistant. These are all popular applications of speech recognition and question answering. Text summarization, so taking a long form document and summarizing that. Chatbots, for example, you may have seen this with customer service. So if you go on a website like Amazon and you want help, you usually get put in front of a chatbot that then routes the query to a human if necessary. Text to speech and speech to text. So this is converting, for example, for people that have disabilities, it converts written text to speech. And then for those that have vision impairment, it converts speech to, hearing impairment, it converts speech to text so they could read the text as opposed to hearing it. And then voice box, text, and audio generation. These are all applications. The one that we will develop together will be sentiment analysis, and I'll touch on that in a second. So these are, again, popular applications: Google Search, Google Gmail, so auto-completing sentences. This is a really magical feature. As you start typing in words as part of a sentence, Google will automatically recommend what the remaining portion of the sentence should be. Google Translate, as you know, Siri, Alexa, we touched on this just a second ago, but these are all the very popular applications that you see. And we're still very early on in the world of NLP. So I think over the next several years, you'll start seeing many more applications beyond the ones that you see here. Now, NLP took a long time to get to where it is today. Part of the challenges involved computational power. Part of it involved discovering new architectures to do NLP better. So neural nets, particularly, I think, opened up the floodgates quite a bit. And part of it was just getting enough investment in the space, because I think there have been a lot of false starts. So successes that weren't fully realized. It was basically optimistic endeavors into NLP. But it dates back all the way to 1950s, the Alan Turing test, you might be familiar. And then many governments have been involved. Russia, many organizations like IBM have been involved. But it's really in the last 10 years that NLP has exploded. So just keep that in mind, that NLP dates back 70 years, but a lot of the improvements have been in the last 10 years. And we'll cover that in just a second. Now, there are different approaches to NLP. So originally when NLP started, it involved using rules. So this is similar to using regular expressions or regex. Basically, what you would do is you would create rules for how to process text, and then you would apply these rules, and that's how you would actually process language. Now, the problem with this is that it's very, very labor intensive, right? So very labor intensive, and it does not scale well at all. Okay, but it's easy to understand. It's interpretable. I think part of the simplicity of rules-based NLP is why this still exists even today. So regex is very, very common when you want some quick and dirty ways of processing language. Now, rules-based has given way to traditional ML, which involves using linguists, so people that study language for a living. They create different rules. They do hand-derived feature engineering. And then what you could do is you could apply a lot of statistics and even some computer science to do this well. So think of using, for example, random forests on hand-derived features, maybe derived by linguists, for example, and then training a model based off of that. So it doesn't involve deep learning, it doesn't involve neural networks, but it involves a lot of hand-engineered feature engineering. This is actually how Google Translate used to work until 2016, when Google moved from classical machine learning to neural machine translation. So they started using neural networks. And that's the reason why neural networks or deep learning has been so popular. It's able to automatically essentially derive a lot of the features that humans used to derive. And then it finds patterns in lots and lots of data, and then solves them in a very elegant way. Now, this generalizes really, really well. It's the best generalization of all of these technologies, but it does require lots and lots of data and lots of computation, both of which are readily available today, because you've seen data explode with availability of data on the web, and you've seen computation explode with the likes of cloud computing like AWS. So it took quite a time to get to neural networks, but it really is the mainstay of NLP today. So with that, let's get started with some basic NLP tasks. We're going to use spaCy to do this. Now, there are other libraries like fast.ai and Hugging Face, but spaCy is the oldest of the three, and the one that has the most commercial applications, at least to date. I know Hugging Face is making a lot of inroads, but spaCy has been around for a bit longer. Now, the tasks that we'll perform, these are typically done automatically today using neural networks, but it used to be that these were done using more classical machine learning approaches. So tokenization, basically taking, for example, a sentence and deriving the most meaningful small units from that sentence. So you could think of this as converting a sentence into individual words. You also treat punctuation marks, for example, and other symbols, but really it's converting the sentences into words. Then once you do have sentences that are converted into words, you do want to tag them with parts of speech. So this is as simple as nouns, pronouns, verbs, adjectives. In a way, a lot of this is very similar to how you would teach a young toddler or child to process language, right? You have them break the sentences into smaller components like words, and then you teach them what are nouns, pronouns, verbs, and adjectives. And the children often do this automatically, but with machines, they would need to be trained on lots of data, but they would start deriving patterns between the different tokens. So for example, I went to the grocery store. I is the pronoun, went is the verb, and to the grocery store is a prepositional phrase that tells you a bit more about what I'm doing, like for example, where I actually went. So that's what dependency parsing does. Here are a couple of examples. Now, this gets a little bit into the kind of grammatical elements of the English language, but you have adjectives, adverbs, nouns, pronouns, and such. And essentially, the machines that we train on basic NLP tasks, they're performing this under the hood. They're learning these properties of the language. Dependency labels, again, really converting the different tokens and deriving relationships among the tokens, right? So simple sentence like, we live in Paris. It's finding the proper pronouns and the verbs, prepositional phrases. So it finds structure in the data. That's essentially what happens under the hood. That's what allows machines to process natural language and then the powerful application that we see, for example, like speech recognition. Now, there are other tasks that NLP does, like chunking, so converting 3 separate tokens into a single token, because they have relationships that are embedded, like New York City. New York City are 3 tokens, but really it refers to one location, so it could get chunked into one token. Lemmatization stemming, it's basically converting verbs and other words into their base form. So biggest into big, slept into sleep, right? So there's just 2 ways of converting so compound words into their simpler forms. And then there are slightly more complex NLP tasks like name entity recognition. So these are finding named people, organizations, locations, dates, and currencies in paragraphs and sentences, and then linking those entities that we find, like for example, we find a named person like George Washington, linking them to more metadata. For example, George Washington is the first president of the United States, right? So that entity linking helps you connect discrete forms of natural language to more richer, more detailed forms of natural language that we have. Now, these are different types of NER tags. Again, NER is a named entity recognition, is a very fundamental, foundational task in NLP. So people, dates, times, and such. Now, these are the 3 libraries. We'll use spaCy to perform the NLP tasks that I just mentioned. First released in 2015, scales very well, supports both TensorFlow and PyTorch. Now, fast.ai and Hugging Face, both of them were built on top of PyTorch initially, but they have compatibility with TensorFlow. Like Hugging Face has compatibility with TensorFlow. They're a little bit newer, but both of them are really well funded and are scaling really well. So I recommend learning all 3 libraries because depending on the organization that you're part of or the research group that you're part of, you may decide to use one of the 3 or maybe multiple portions of the 3, but all 3 are very, very active in the NLP community today. So with that, let's go to a coding environment. We'll actually go to Google Colab, which is a great coding environment. I'm sure many of you have used it, but a couple of quick things. Google Colab is provided free by Google. We use cloud compute to actually perform the functions, but it's really good for basically doing the compute in the cloud for free and then sharing your work with peers. So let's turn to that and get right into it. Let me go ahead and share my screen here. Just give me 2 seconds. I'm going to try to find where I place the window. Okay. So here we go. Now, as I said, this was originally derived for ODSC as part of the curriculum that I teach there. You can find more on ODSC and the AI Plus training program. For now, let's just turn to the module as part of this course. All right, so this sets up the Colab environment. It loads in necessary libraries and the necessary data, and then installs spaCy, right? So spaCy is what we use to actually perform the basic NLP tasks.
Hi, Uncle. Are you looking to share the?
Go ahead, Stephen.
Are you looking to share the Colab link?
I think I'll have to actually make it shareable.
Okay.
But I can share the Colab link.
All right, sure.
But I will after the course, if that's okay.
All right, perfect.
All right, so again, this just loads up the libraries and loads the data, installs spaCy. And then we could load the spaCy library here. So import spaCy, loads the library. And then we'll use this to perform the task that we just mentioned. So tokenization, right? So we take a sentence like "we live in Paris," we feed that into the NLP tokenizer that we used from spaCy. So this loads up spaCy's model, right? So spaCy's, this is essentially the English model that spaCy has on core web data, and it's a small version of their model. So this spaCy model is what we use to tokenize the sentence, and then we can print the various tokens in the sentence. So there are 5 tokens, and then you can see the individual tokens in the sentence, which are "we live in Paris," period. Right. So it breaks the sentence into their subunits, which are these tokens. We could also do this on a larger and more complex data set. So we'll actually use Jeopardy questions. We do some just quick data processing here. So we strip white space, we lowercase the words, and then we reduce it just 1,000 rows. And then we could tokenize all of the Jeopardy questions. So basically do data question, which is the questions in the Jeopardy data set, and we apply the NLP model, right? So you can see the data here. It shows you the questions here and the answers. And then we created this this column called question token. So taking the questions and tokenizing them. So you can see the first question here. And you can see the tokens that get derived, right? So first question is, for the last 8 years of his life, Galileo was under house arrest for espousing this man's theory. That's a question from Jeopardy. And then since we already tokenized this, it shows you the tokens from the first question. So first, for is the first token, the is the second token, and it goes on and on. Right, again, so it converts the sentence into more meaningful subunits, which are necessary when we feed that into an NLP model. Part of speech tagging, it basically takes the tokens and tags them with relevant parts of speech, which I showed you in the PDF a second ago. So for example, for is an add position, right? So basically, what metadata would help us analyze for? It's this. So a couple of easy ones, like years is a noun, right? His is a pronoun, life is a noun, Galileo is a proper noun, so it's referring to an individual, right? So again, adds more metadata. Now this is going to be too much information because nowadays a lot of this is done automatically by the deep learning model. So you don't necessarily need to do this yourself, but it's important to understand just how machines take in language and how they actually perform the tasks necessary in order to solve more complex problems. Dependency parsing, again, it's creating structure out of the tokens. So it's tagging it with relevant dependency tags. And then you could visualize the dependency parse, which is here. So different things get linked to each other depending on where they fit into the English grammatical structure. So you can see for the last 8 years, they're part of this one block, right? Because that's a prepositional phrase. And then you could see, other prepositional phrases like was under house arrest, right? So these are all connected. And then you have a prepositional phrase for espousing this man's theory. So again, all of them are connected. I think this will be clear when you go through this notebook yourself, but it creates structure from the underlying tokens. Now chunking, we did this. So my parents live in New York City. You can see that there are 2 chunks here, my parents, which could be grouped together, and then New York City, which could be grouped together. So again, chunking is an element of basic NLP that happens under the hood. Lemmatization, it creates base forms of more complex compound words. So for a lot of this, the original token and the lemmatized token are the same, but for some, these are a little bit different. So years gets converted to year, espousing gets converted to espouse, right? So it creates the base forms of the original words. Again, it simplifies the tokens, which makes it a little bit easier for the machines to process the natural language. Named entity recognition, we covered this a second ago, but it finds the named entities. So in this sentence, so the sentence is George Washington was an American political leader, military general, statesman, and founding father who served as the first president of the United States from 1789 to 1797. So there's several named entities here. And the named entities that we have are George Washington, which is a person, American, which is, it gives more character to who George Washington is. You have an ordinal, the United States, which is a geopolitical entity, and then dates 1789 to 1797. And you could even visualize this. So George Washington is the person, first is an ordinal, the United States is a GPE, so geopolitical entity, and then this is the date. Now this makes it easy for you to see what elements the spaCy model was able to find from this one sentence. And then you could link these entities to richer metadata using, for example, like the Google Knowledge Graph Search API. Now you do need an API key from Google to do this, but you can link George Washington to more relevant descriptions of George Washington. And in fact, when we did this, it actually mapped it to the wrong George Washington. So there's a George Washington University in the US. So it mapped it to the wrong one. So you do have to be careful about entity linking, and you can improve this model by feeding in more metadata. So you could say George Washington is in the context of US politics or is in the context of US presidents. And then when you link it to Wikipedia, it will actually link up to the George Washington as a president entry as opposed to the university that you see here. So these are just basic NLP tasks. I'll leave time for questions at the tail end of the course, but let me dive into module 3, because these tasks that I just showed you, a lot of these are done automatically with large pre-trained language models that most of you will use if you're doing NLP in an applied setting. But this was essentially what led us to where we are today. So it is important to understand what the foundational tasks in NLP are. So go back to the PDF. So state-of-the-art NLP. Specifically, this module will build a sentiment analysis model on IMDb movie reviews. So for those of you that might not be familiar, IMDb is an aggregator of movie reviews, similar to Rotten Tomatoes, but IMDb has been around for a very long time. And it's great because they have movie reviews that reflect different sentiment, positive sentiment, neutral sentiment, negative sentiment on all sorts of movie reviews across many different types of movie categories. And we'll actually build this model using fast.ai. So one of the other 3 open source NLP libraries, along with spaCy and Hugging Face. Now in this module, we'll use pre-trained language models. As I said, this is the way that modern NLP is done today. So you're using large pre-trained language models. These pre-trained language models are essentially very large neural network derived models. So they use large neural networks that have been trained on lots and lots of data, hence the word pre-trained. And these language models learn the properties of language in the same way that you just saw with the basic NLP tasks, except these models have learned on lots and lots more data. So they learn important properties of language automatically without human feature engineering, without any rules that humans have to create. So it's done using just computers. And then the beauty of the language models is that once they've learned important properties of language, they can be fine-tuned and they can be used to perform transfer learning. So essentially, you can use the language models to perform a variety of tasks like sentiment analysis, text summarization, predicting sentences that come forth next. You could use them to do a variety of downstream tasks. And that's what led to the big breakthroughs in NLP. The fact that pre-trained language models could be used to perform lots of other downstream tasks very, very easily. All right, so why is this relevant? Well, if we had to do basic NLP ourselves, we actually would need lots and lots of humans, so practitioners, to do these tasks manually. It really would make NLP very hard to do and very hard to scale. And so we do need to have computers learn from data by themselves and then perform complex tasks. And that's essentially what neural networks do. They learn from data on their own to perform tasks that would have otherwise had to have been assisted by humans. And so the latest approaches use this architecture. It's very custom architecture. It's called the transformer architecture. And the transformer architecture relies on attention mechanisms. So these innovations, they come about mostly in 2016, 2017, and 2018. So in that 3-year window, we had attention mechanisms that were then stacked on top of one another. And attention mechanisms essentially point to where in a particular paragraph or sentence the model should attend to, hence the word attention. And the transformer architecture basically took these attention mechanisms and packaged them together, so stacked multiple attention mechanisms together. And that led to large pre-trained language models that we have today. Now, these are a lot of technical details that I'm just glossing over. We don't have enough time to go through all of this in great detail, but just know that if you want to go deeper into the theoretical and conceptual elements, you will want to study the transformer architecture. So with that, let's talk about pre-trained language models. So machine learning in general, it's a process of machines learning from data to improve the performance on a specific task. Right, so the more data the model the model learns on, the better its performance will be over time. And the model essentially learns these parameters, the weights and biases that allows the model to perform the task really, really well. Now, once the model has been trained to sufficient level of performance, it stores the knowledge, and this stored knowledge is vital. That means that the model can perform inference on future data and get reasonably good performance so long as the data that it performs inference on is similar to the data on which it was trained on, right? So the stored knowledge aspect is super important. The fact that it's able to learn automatically is really, really important. That's what makes machine learning so powerful, so capable of doing these complex tasks. Now, neural networks are a particular type of machine learning. They rely on a neural network. So these are different nodes and layers that help the essentially the model learn different representations of the original data. So at its core, you have input data, and then you have output data. So input layer and output layer. And the model is learning how to organize the input data into better representations so that it can perform the task at hand and derive the output that it tries to optimize for. So this hidden representation, this representation learning is what neural networks are very good at. So how do we get to using neural networks to solve NLP problems? Well, neural networks are very good at learning about properties of the original data, right? So think of neural networks as learning about important properties of the original data such that the important properties that they learn make it easy to solve a downstream task. So when you try to solve language modeling, and language modeling is a particular task in NLP. In language modeling, you're trying to predict the next likely word in a sentence. So for example, how are, like that sentence can have multiple words that come after how are, but some are more likely than others. For example, how are you is more likely than how are they, right? So you is the most likely word. And by learning on lots and lots of data what the next likely word should be, could be, basically the model learns important properties of data. Things like how to tokenize more intelligently, what the parts of speech should be, what the dependency parsing should be, how words should be lemmatized and stemmed. That's what neural networks do. They learn important properties of natural language such that the properties that they learn help them predict the word you instead of they when the preceding words are how are, right? So how are you is more likely than how are they. So again, it learns important properties of language so that it's able to predict what the next likely word will be. Now, the interesting thing is that language modeling is, you don't need annotated data to do that. You could actually just feed large corpuses of text. For example, you could feed all the works of Shakespeare into language modeling, and the model has already the annotations embedded into that corpus because it can mask the next word that comes in a sentence and then try to predict what that word should be. So it's able to learn on its own on basically data that hasn't been annotated by a human. This discovery, the ability to take language models and train them on large corpuses of natural language, and then unfreeze a few layers of the neural network. So typically the layers that you unfreeze are the last few layers, and then train that, essentially that pre-trained language model on a downstream task like sentiment analysis. That's what led to the latest revolution in NLP. The reason why NLP has done so well in recent years. It's taken these pre-trained language models, trained on large corpuses of text that are available on the web, unfreezing the last few layers, and then performing this transfer learning, so transferring the properties of language that the model has learned from doing language modeling, and then using those properties, transferring them to a different task like sentiment analysis. And that's essentially what we'll perform here in a second. So here's transfer learning. You take large pre-trained language models to perform many different types of NLP tasks. It is by far the fastest way to do NLP today. It is the way that you should be doing NLP if you're doing this in an applied setting. So essentially, transfer learning, you take the first few layers of the pre-trained language model, which have learned useful properties of the data, and then you use those properties to then just train the last few layers of the neural network on a downstream task that you have, right? So it allows us to more quickly solve the task at hand without having to annotate data from scratch. Now, this is really, again, net language modeling in more detail, but it takes a sequence of words and tries to find a probability distribution for the next possible word in that sequence. So language models learn the features and characteristics of language on their own without any explicit annotations, as I said. So it can be trained on massive corpuses of data without a lot of data prep. And then essentially what we do is we can take the language models and we can fine tune them on specific corpuses. So imagine you had a large language model that were trained on Shakespeare. Now, Shakespeare is not very good or not very well fine tuned to solve tasks that might be related to the financial corpuses. So how do you take a model that's been pre-trained on Shakespeare and then fine tune that on financial documents so that you have a fine-tuned language model that can do sentiment analysis better on financial documents than it would have done had you just used the original pre-trained language model on Shakespeare. That's what fine-tuning is about. It's a way to eke out better performance from the language model that you originally had. So we'll actually do some fine-tuning here, and you'll see it in action. So this is the work that we'll perform in the next 10 minutes. We'll take the IMDb movie reviews data set from fast.ai. So again, this is already preloaded, ready to go, has all the movie reviews from IMDb. And we'll train a sentiment analysis model. Now, how are we going to do that? Well, we're going to take a pre-trained Wikipedia language model. So this is a language model that's been trained on lots and lots of Wikipedia articles. And then we'll unfreeze the last few layers and train it to perform sentiment analysis, right? So this is a Wikipedia language model used to perform sentiment analysis on IMDb movie reviews. Okay, so this is a form of transfer learning. Is we're transferring the properties that this model has from training on Wikipedia articles, and we're then using the pre-trained properties to more quickly build a sentiment analysis classifier on IMDb movie reviews. That's one way of doing this, and you will see really good performance. That's the reason why using pre-trained language models should always be the first way you approach the tasks you have. But the second way we're going to do this, and this is step 3, is we're going to take the pre-trained Wikipedia language model. We're actually going to unfreeze sorted layers of it, and then we're going to train it on IMDb movie reviews. So you can think of this as taking a Wikipedia language model and fine-tuning it on IMDb movie reviews to have a more fine-tuned IMDb language model. And only then will we then train a classifier to perform sentiment analysis. Right, so it's similar to what we do in 2, except the thing that we do that's different is instead of going from this Wikipedia language model to the IMDb classifier, we actually perform this intermediate step of taking the Wikipedia language model, fine-tuning it on IMDb movie reviews, still have a language model after all of this, but then we use it to perform the specific task downstream, which is text classification. So this is sentiment analysis on IMDb movie reviews. And what you'll see is that while step 2 has really good performance, step 3 will have even better performance because you use a fine-tuned version of a language model before we perform transfer learning. And then we can see the results. Okay, so with that, let's go and turn to the coding environment and cover some of the material there. Now, I will share these notebooks, so you should have access to these notebooks. You'll be able to dig in a bit more as we go. So sentiment analysis on IMDb movie reviews. As you can see, this is part of the Applied Natural Language Processing series on ODSC. But here are a couple of critical components. We load in fast.ai, so we install fast.ai, we upgrade it, and then we prepare the data. Now, the data preparation is basically loading in the IMDb movie reviews from fast.ai. Okay, so we download the data, and I've already run this code because it does take a bit of time to download the data, process this, train the model. It'll take a few hours to do, but I've already run this so you can see the results. So here is the data that we've loaded in from fast.ai. Now you'll see certain tags here and there are markers for the text, but essentially this is the text, this is the IMDb movie review, and it tells you whether it's a positive or negative. So we do have labels. So we can evaluate the performance of our model using these labels, and we'll need these labels to train the model anyways. But you can see the movie review here. It's kind of hard to unpack because there are a lot of metadata tags that are part of this mix, but we can see the movie review here in more detail in a second. So for example, this movie review here, 6, says how strange the human mind is, the center of activity wherein perceptions of reality are formed and stored, and in which one's view of the world hinges on the finely tuned functioning of the brain. This most delicate and intricate processor of all things sensory, right? So it goes into the movie review by describing certain elements of it. But it has these tags, which are really important, that the model has performed as part of the text pre-processing that was done. So let's do a couple tasks. One, let's build text classifier on using the Wikipedia language model. So here we're taking the Wikipedia language model and we're going to fine tune it to perform text classification, particularly sentiment analysis. So we're not fine tuning the language model. We're just taking the language model and we're building a text classifier off of it. And you can see that after a few rounds of training, the accuracy rises from 82% to about 93%. And you can see the results here, right? So you can see basically the ground truth, which is the category here, and then the prediction, which is a category underscore. And you can see in most of these instances is right. Some instances we get it wrong. So for example, the ground truth here for this review number 3 was positive, but we actually marked it as negative. However, the sentiment analysis model, we can run on lots of different sentences. So here, for example, if we want to perform inference, we could say this movie was wicked. And the model that we trained is able to predict this as positive, POS, with a pretty high degree of confidence, so about 89%. And then there's another sentence, what it did, we predict that to be negative with really high levels of confidence, so 98%. Okay, so again, trained the sentiment analysis model on IMDb movie reviews using fast AI and then performed inference. Now the training process, because fast AI is such a high level library, it loads a lot of the things we need very, very quickly. So it loads the data here, DLS, it loads the model, this LSTM model. So instead of a transformer-based model, we're using LSTM. It's a little bit lighter to use to train this. And then it feeds in certain hyperparameters. For example, this dropout multiplier, and then has a metric, which is accuracy. So with this one line of code, you're able to train a sentiment analysis model on IMDb movie reviews using the Wikipedia language model that we just mentioned. Again, it happens super fast under the hood, abstracts a lot of the more nuanced things that would need to happen to make this possible. That's why fast AI, Hugging Face, and spaCy are so good. Now let's turn to fine-tuning the language model on the IMDb movie review data set. Now this is very, very similar. So you still load in the text, right? But the text and the text prediction, so the label, is just one additional token. So look at this here, 0. You see the original text ends with could never duplicate. And then the text underscores could never duplicate thinking. So it just loads in one more additional token above and beyond the original text. This is the reason why language modeling is so good, is that you don't need to go and hand annotate a lot of this data. It just uses the data that we have and moves the window just one more token to the right, so you could see what the prediction should be. So for example, he has to clear the room, and then you see one additional token. He has to clear the room off. And you do this over and over again for every single kind of sentence or series of tokens, and then you train the model on it. So this Wikipedia language model is trained on IMDb movie reviews, and you have a fine-tuned version of the language model, right? So instead of using a Wikipedia language model, we're going to be using an IMDb derived language model once this exercise is complete. So here we go. We take this and we train the language model on IMDb movie reviews, and then we build a sentiment analysis model. And when we build a sentiment analysis model, so this just fine-tunes the language model, and we save the model, right? So we save the learner, and then we unfreeze it, train it some more, and then we have a fine-tuned language model, and then we train this fine-tuned language model on the data that we care about, which is the IMDb movie reviews, to perform sentiment analysis, right? But here, before we get to the sentiment analysis bit, let's actually look at this language model. So we save the fine-tuned language model on IMDb movie reviews, and we can use it to predict the next word in a sentence. That's what language modeling is. It predicts the next word in a sentence. So this IMDb derived language model says, I like this movie because, and then it predicts the next token. And you can see this, we run it twice. I like this movie because it was a great movie for anyone to watch for their own. This is a thriller and not a thriller. So again, the further you get, the more nonsensical it gets, because this model isn't really optimized for natural language understanding and natural language generation. This is an open area of research. You do see the likes of like GPT-2 and GPT-3 by OpenAI, but it is an open area of research. But it typically does the first few tokens really well. So for example, if you feed in, I like this movie because, you could see the sentence, I like this movie because it was consistently funny. That's a super coherent sentence. There's a legitimate reason for liking a movie. Then it gets a little bit more incoherent, not entirely, but somewhat, right? So it was not the same as Ed would. I'm not sure if that makes a lot of sense. But then the next words do make sense. It was excellent. The acting was great. The acting was so good, and the plot was weak. So this is this is where it gets a little bit nonsensical. It loses some of the reading comprehension. But you can see that we had the Wikipedia language model fine-tuned on IMDb movie reviews, and then you have an IMDb derived language model. Then you could train it for sentiment analysis, which is really going through the steps that we did earlier. And you can see that performance actually improves to, let's see here, we train it over a few different layers. I mean, sorry, a few different epochs by unfreezing layers of the neural network a little bit at a time. And you can see that the accuracy moves from 93% closer to 94. Now, had we trained it for longer, I think we would have gotten better performance. But the idea is you take a Wikipedia language model, you train it on language modeling on IMDb movie reviews, you get an IMDb movie reviews language model, and then you build a sentiment analysis model, and it basically boosts the performance by a little bit. And you keep training, right? So, for example, you unfreeze the whole model, continue training it, which is, by the way you should train neural networks that are pre-trained. You should unfreeze a few layers at a time, and then train it and train it and train it until the whole model you can unfreeze and train it. And here we get to a performance that is about 93.7. Again, maybe there's better performance by handling this a little bit better or training it for longer, but you can see that it boosted the performance by at least 1 whole percentage points when and when you're talking about accuracy that's already pretty high, each percentage point does matter. So the fine-tuning the language model does eke out a bit more performance. So that's really the bulk of the workshop here. I mean, we covered NLP over the last 70 years. Very quickly, we talked about some of the applications that have happened in the last 10 years specifically. We covered basic NLP tasks using spaCy, and then we used fast.ai to work with more state-of-the-art approaches to NLP. So pre-trained language models, performing transfer learning, fine-tuning language models, training specific applications like sentiment analysis, which in this case was for movie reviews. So with that, let me turn it over to Stephen. I think we're going to open this up for a Q&A session. And then what I can do is, again, I can share a lot more materials on this. You also have it in my book, so there will be a lot more. But again, I wanted to build some intuition about NLP and state-of-the-art NLP with this workshop.
All right, thank you so much, Anko, for your session today. I'm just going to go to the panel session, chat panel. Viewers, if you have any question at all, you can start asking them. Any question at all? And so obviously we're also going to share details to of the workshop as well as the full recording to you, probably most likely by either by the end of today or most likely by Monday or so. So yeah, and that would also include the links to the notebooks as well. So kind of note that out. Any question? Anyone? Okay, so far there are none. But yeah, if you have any question, of course, through the post-event email, you can reply to them. Maybe if you're watching this at a later time, you can reply to the post-event email. So we will get that to Anchor to treat, and then get back to you with a proper response. Once again, this is Port Harcourt. This is AI School Africa, and I've kind of pinned here. We have our membership sign up on community updates. We have monthly webinars. Not that that's going to happen next month, but surely we have something occasionally around having monthly webinars, workshops, and pretty much sessions with experts across the world. So you can definitely try signing up for our community updates so you know when the next webinar will hold and so forth. So thank you so much, Anchor. Do you have any final thoughts you want to share with our viewers?
I think this is mostly it. Now, I will say that we do have a lot more materials that we could share. So if you have any questions, please reach out. So as I said, I have my books on Amazon, O'Reilly, Safari, but I also have free notebooks and free code snippets and samples on GitHub. So it's a great resource for you to catch up on a lot of this. If you do want to focus on trends in NLP, there is my blog, unclersnewsletter.com. So you can find me there. Happy to answer questions, happy to help people on the journey that they're on. Just reach out. Feel free to just email me directly.
All right, perfect. We are going to be sharing all of those in the post-event email, all the resources that Ankur has listed, so that you can catch up with this properly. We want to ensure that you can think about NLP for your organization, think about NLP for your project, and where have a clear path of where to start. Hence one of the reasons for this session. So thank you so much once again, Ankur. Thank you so much once again, viewers, for joining this session. We're now going to be ending the session, but rest assured you're going to be receiving more emails from us on the next steps from here. So we will have a great time, everyone, and bye. We're in the stream now. Bye.
Thank you, everyone. Bye.